I think we got there. Yeah,
Yeah,
look at
perfect.
that. Let me just make the windows look right again on
Whoa,
my
it's
side.
moving,
It's moving. Yeah.
unlike honeycomb.
Uh, we don't need to talk about how the graphs at the bottom get there. Um, yeah. Hello everyone. Thanks for joining me today. I'm going to share a presentation I originally gave at Everything Open 2025 in Tantanya, Adelaide. I'm presenting today on the lands of the Wathaurong people of the Kulin Nation, where I live in Geelong, which is about 60 kilometres south of the lands of the Woiwurrung people and the city of Naarm, or Melbourne, in Victoria, Australia. The Wathaurong and Woiwurrung people are the traditional owners and custodians of these lands. They've been hunting and fishing here, living and working here for more than 40,000 years as part of the longest continuous culture on this planet. And just as we are coming together today to share stories, the people of the Kulin Nation tribes came together too. I pay my respects to elders past, present, and emerging, and acknowledge the continuing connection to land, waters, sky, and culture of Aboriginal and Torres Strait Islander peoples across Australia. I also extend that respect to all First Nations people on the call or watching the recording. Aboriginal and Torres Strait Islander sovereignty was never ceded. This always was, always will be Aboriginal land. What happened in production? And how can we use OpenTelemetry to solve it? We'll get to what happened in production in a moment. Who am I? My name is David Bell. I'm a DevOop, so I mostly write YAML and yell at GitHub Actions for a living. But before the cloud and CI/CD, I was an ops person. So I'm working on turning my trauma into my profession by being an observability fanatic. I'm obsessed with building a shared understanding of happening inside the systems built and run by the teams I work with. That often means writing some pretty questionable code in languages I'm well out of my depth in understanding. We'll see some of my not so handy work a little later. I apologize in advance. And I have a spicy brain. And that means these sorts of systems and these kinds of approaches to problem solving really scratch an itch for me and provide no shortage of opportunity to pull things apart. Today, we're going to follow the story of a mysterious long-running incident. We'll talk about what is observability and the concept of knowns and unknowns. I'll subject you to my take on the apocryphal three pillars of observability. There's a chunk of theory crafting about OpenTelemetry, and then we'll bring it home with the fine print. I'll share a worked example of how we can instrument the system from today's incident, and with any luck, we'll resolve our incident. Hopefully. This is a work of fiction. This isn't a presentation about anything at my current day job. I work at a bank. They're not so stupid to even think about suggesting talking hypothetically about a situation like this. I don't know of any systems that work like what I will describe, or incidents that have gone on like this one. This isn't the Don't Get Fired Challenge 2025. Entirely coincidental and highly unlikely I'd get nearly enough of the details right on recollection. We are Microliths R Us. We're purveyors of fine event-sourced Internet of Things microservice-backed architectures. And we've just finished a trial with our 59th client, our latest new big client. And I hope you don't mind that I'm on call for them today. Um, we should be fine. These systems are rock solid. Yes, we've snagged a contract with Honeycomb Champions Incorporated. That's you. They've just finished a lengthy trial with a single device and loved it. So they're rolling out to a selection of their fleet. Well, we wait till we get to the details. Here's sort of a TLDR on the system. You're an Internet of Things device and you're using an event sourcing model. So you ask us for the next chunk of events newer than your current state, and we gladly return them to you. You do this on repeat. Maybe there's a lot going on, or you're just a bit behind the times. Eventually, things stop happening, or you catch up and we send back less. So you'll be back a little later. But sometimes requests time out, and you need to ask again. Can you see where this might be going? Yes, something is broken. I don't know if this is coming through, but it's the page duty. Something's broken. Frere Jacques. Um, yeah. Yes, something is broken. Well, we can see from the metrics on the screen that they don't look happy. We can see a big old spike in errors, and the response time went up massively. We can see something is wrong, but it doesn't really tell us much more. But what about the logs? It's all going great until it's not. Like, there's nothing particularly useful about what went wrong here. Well, I guess we'll just have to hit. We haven't hit whatever this is yet to have added a log message for it happening. Microliths R Us went on like this for quite a while. 2 p.m. would roll around, events backend would fall over, straining under the load. Sometimes recovering quickly with barely an increase in latency, other times totally locking up the database, requiring a lengthy crash recovery. I spent many hours as an amateur database administrator convinced more disk or memory might save us. But we were trialing a new approach and a new tool, observability and OpenTelemetry. Microliths R Us had already added it to some platform-owned systems to great success, but there hadn't been much movement in convincing product-owning teams. After all, their systems were clearly working quite happily in production. Our synthetic monitoring told us so. Sound like a familiar story? We'll return to our story after a little bit of theory. You know, the actual technical stuff you probably came here for. Who or what is Ollie? Charity Majors is my personal idol in the observability space. She introduced the term observability, often written as O11Y and pronounced Ollie, in the style of Kubernetes being K8S or Kates. Charity paraphrased mechanical engineering and control theory to position observability as the ability to understand what is happening inside the system, any internal state, simply by asking questions. Some of you may already be familiar with this sort of table and the concept of known knowns and unknown unknowns. Knowledge is what we already know about our system. These are hard facts we collectively know. Awareness is what our current or previous practices might be able to tell us about the state of our systems. We're aware of things we ask about. Request volumes, average times, CPU usage, so on. We all have biases. It's important in any context to identify them, be aware of them, and challenge them. Ignorance feels harsh here. Opportunity feels a bit corporate. Interesting stuff. Teach me something new. The observability industry is obsessed with the notion of observability having 3 pillars: metrics, logs, and traces. Conventional wisdom is that you need all 3, and that if you get the balance just right, then you'll reach DevOps enlightenment. So let's start with the first of the 3 pillars, metrics. Can you count on them? Maybe that should be metrics. But we all know them and are familiar with them. Minimums, averages, maximums, sums, maybe an exotic percentile measurement. Our cloud infrastructure loves to spit them out, so it must be the way. Yes, but also no. They're pre-aggregated. That means they're bundled together in increments and presented as an average or percentile, and maybe have a very limited number of dimensions. Therefore, they can only answer predefined questions that fit those aggregations and dimensions. They have no connective tissue between individual metric points. Each is just a single data point. it can't tell you something like the average. It can tell you something like the average latency over this 60 seconds was 500 milliseconds, but were some really fast and some really slow? Sure, you could add a couple of minimum and maximum metrics to give you that, uh, but you can't tie that together with any other metrics, such as error rates. You only know the ranges independently. You can't drill down on a metric. Yes, the load balancer returned 1,000 HTTP 500 errors, but what were the paths associated with each? I guess we'll have to check the logs to find out. But they're not totally without use. We can answer questions we know about, such as how many errors were returned or how quickly a message leaves a queue. We can draw some pretty graphs on dashboards and make inferences about the shapes of the lines. We humans are great at picking out visual patterns. We can report on things like daily volumes, management, lava summary. They're great for things we have knowledge or awareness of, but they fit and feed our biases and tell us nothing about interesting unknown unknowns. What about logs? We said we'd need to check those to see what endpoints were causing those 1,000 HTTP 500 errors. They're often boilerplate logs from the framework we're building on, some bespoke format, or haphazardly sped out strings. Logger.info, starting request, console.log, retrieved 1,000 rows, and so on. Some of us will have the misfortune of having learned that text streams are the universal interface, so we'll likely be fortunate to be comfortable enough to break out sed to make sense of those logs. There are potentially many log lines for each piece of work. If you're lucky, they're tied together with a common identifier used in a common way across all log lines, like a request ID or a field prefixed on each log. Unlikely. You've got to break out grep. Each of those log lines might have some useful data in them, or they might not. If it's there, you've got to tease it out by hand. Break out the entire GNU toolkit. Grep, sed, cut, pipe, sort, unique, and chuck some regex in there for good measure. If you have no schema or structure, it's hard to have an index to make searching efficient. I know I've previously downloaded system logs to parse locally rather than waiting for the logging platform du jour of previous employers because the thing was just too slow, needing to extract the same fields again and again. Structured logging, however, is fantastic if you can pull it off. What do I mean by that? As an example, I mean emitting all your logs as JSON with clear and consistent key value pairs for all your fields. But all that logging data is expensive, especially for you to process and store the field names on every single one as well. I'm sure anyone who's worked somewhere with one of the large incumbent logging platforms knows the pain of either administering that platform or having the administrator come to tell you to stop logging so much. Log everything, find nothing, die unfulfilled. They too have a place, namely audit logging and security events. Stuff you need to get written down in a way that will block execution if it can't record the log. When it comes to containerized applications, it's common to output logs on standard out. If you can't output on standard out, something is probably very, very wrong. Then you shouldn't, or possibly even can't, process the request. If you can't log the sign-in request, then the sign-in request shouldn't happen. 2 pillars down, 1 to go. Tracing must be the one true pillar then, no? Maybe, but historically, not really. It's often kept in a separate tool, away from where you're used to seeing your metrics on a fixed dashboard, and your logs in your expensive, either contractually or operationally, logging tool. So you might get an alarm from a metric, such as error rate or response latency, which might give you a rough timestamp, plus or minus a minute. Then you go and look at your logs, which might give you some idea of the methods and endpoints involved, and a more accurate idea of the time of the problematic requests. If you're lucky, you'll have a tracing tool of some sort, and you might even have a trace for one of those exact requests. But does it have the business context that's relevant to you? Has it been molded to your use case? Or does it just tell you what you likely already know, that you mostly wait on the database to return responses? And if it does have those things, my experience has been that it's then typically tuned to only look for bad events, errors, latency, that sort of thing. But how can you know what's making it a bad trace if you have no baseline data available from the same time? And given it's historically been mostly used to look at bad requests, and the purpose of a system is what it does, then that's all tracing systems often want to show you, the bad traces. There's limited capability to use the data in other ways, such as searching across it. Apologies to those of you I've now earwormed with Frozen 2, but we're going into the unknown unknowns. We're here to dig into the interesting stuff going on inside our system, to be able to understand the internal state from outside just by asking questions. So let's take a look at OpenTelemetry. Uh, OpenTelemetry, often shortened to OTel, is a project and open standard maintained by the Cloud Native Computing Foundation, the same folks who oversee Kubernetes. This project will fit so many pillars you wouldn't believe. It's got you covered on metrics, logs, and traces. Sorry, I just have to say, I'm really enjoying watching Jess's reactions here. It's
Well, that
thank
was
you.
really funny.
I'm glad it's landing. Um, it has a wide range of languages supported, including Python, Java, JavaScript, Node, and Web, Golang, and Rust, to name some of them. And while I can't speak for all the supported languages, the ones I've used, I definitely consider like batteries included with auto instrumentation. Auto instrumentation is applied differently depending on the language, but think of it like a set of wrappers or hooks into commonly used libraries and SDKs that provide context about what your application is doing without writing a single line of code to get it. An example of what that looks like is knowing for free how much time you're spending waiting on a database call without needing to handle the timers yourself, or tease out which database or connection or user or table, or normalize the query that we used. They're all added for free to the automatically created spans as attributes. It's also super simple to get started. You can often enable it without modifying a single line of application code, just by calling your app via a wrapper or providing an agent. I've previously rolled out auto instrumentation to an entire fleet of Java microservices by adding it into the in-house Docker base image. It was incredible the amount of scaffolding that put in place for building on top of, creating incoming and outgoing request spans that we could enrich with our own business context. Those auto instrumentations also handle propagation of trace context between distributed systems, meaning you can share the same tracing across disparate systems written in multiple languages. Distributed tracing is commonly handled by request headers, passing along the identifiers for the trace. The auto instrumentation libraries know how to serialize and deserialize these values and handle injection and retrieval of the out of those auto instrumented libraries. And there are heaps of vendors that support it, so you can try sending the data to multiple to find the right fit for you. I'm personally using Honeycomb today, but if they stop keeping pace or a better player comes along, well, so OTel tracing's where it's at. But what is it? How does it work? Traces are DAGs, directed acyclic graphs. That is, each node can only point to a single other parent node without any loops, and at the top we've got a node with no pointer elsewhere. The nodes in the DAG are spans. A span represents a chunk of work, a literal span of time. You can think of spans as a fancy structured log, a big old pile of JSON with some required fields. A name, a start and end time, and the span's context. That is, its trace ID, the parent span if it has one, and its own ID. Typically, that's all handled by the OTel SDK for you, but you can dive in and do it by hand if you need to. Those fields are referred to as attributes, and your spans can have many attributes. Some are provided by the auto instrumentation. Some you can provide yourself based on your application's specific business domain context. We can have both high cardinality and high dimensionality. Cardinality refers to how many values can be assigned to or tracked by a single field. A high cardinality field might be a ticket number or invoice number or seat number or height. A low cardinality field might be attendee species. Is anyone's cat on the call? We are all online, possibly. Dimensionality cuts the other way and is how many attributes a single span might have. The wider you go, the more enriched these spans, the easier it'll be to uncover the unknown unknowns. We can have high dimensionality, meaning we can have as many attributes or fields as we like. There can be a limit. It's up to the platform you're sending to. Honeycomb, for example, accepts no more than 2,000 distinct fields on a single event. But all things in moderation. OTel tracing won't solve all your problems. Just as with your logs, you shouldn't stick PII in your tracing. That should really go without saying, and yet. I don't think this is a replacement. I also don't think this is a replacement for your business analytics engine or your data lake. But that's also not really my bag, so maybe there's something that does actually scratch both itches there. There's no guarantee on delivery. This is a tool designed to help you when your system is failing. You don't want to discover it's the cause of that failure, so it gets itself out of the way when resources are contended. The trade-off here is between system health, but the occasional mistrace, or total outages, but more aggressively trying to track everything as it all falls over. That means it's no good for those audit and security logging we talked about. OTel is non-blocking by default, but audit logging should probably be blocking. But we can lean into the lack of guarantee and build on the fact we might not get every single trace for every single request and use sampling to manage our data volumes. We don't need every trace. Sampling will do. Just like getting a blood test, your doctor doesn't need to drain your body to check your iron levels. Just a little goes a long way. There's two approaches we can take, heads or tails. Head-based sampling is deterministic, based upon the trace ID generated before we do any work. We can configure what proportion of IDs should be included in our sample, and that decision can be propagated throughout our system. Tail-based sampling is non-deterministic. We don't know which traces or spans we will or won't keep until we look at what's available after they're generated and make a decision. Maybe we'll keep 1 in 50 traces from fast, successful requests, but 100% of anything slower than 10 seconds or that has an error anywhere in it. When you're starting out your OpenTelemetry journey, I recommend keeping it simple, using head-based sampling, until you get a handle on your span volumes, you can always tune the sample rate in the event of an incident that requires more data. Yeah, that's fair. So, what's going on over at microservice? Can we get some of that sweet, sweet observability for events backend and find out why the service fell over? We're going to take a quick look at the instrumentation done for events backend, starting with auto instrumentation. We'll need just two packages, OpenTelemetry distro and OpenTelemetry exporter OTLP. Distro installs the API, the SDK, and a couple of tools, including OpenTelemetry Bootstrap. The exporter is required for being able to send our spans somewhere, using OTLP in this case, which is the OpenTelemetry protocol. Bootstrap will check your application and collect the various other OpenTelemetry auto instrumentation packages you can use based on what you're already using in your application. You can use it with your existing requirements.txt or entirely standalone. Here's the list of packages it installed in this particular app where it's providing auto instrumentation. You can see Flask, MySQL Client, SQL Alchemy, and requests. So that's good that we can leverage auto instrumentation on those without having to touch the code for those at all. But there's also a few we don't really need that I probably should have removed. I'm doing nothing with Ginger 2, SQLite, or WSGI at this point. But I suspect they're just coming along by default with Flask and SQL Alchemy. And here's the required configuration. Service name, the protocol you want to output with, and where you want to send it to, and potentially any authentication headers required. It's no secret, I like Honeycomb, and so this is what my config looks like right now. I almost wish there was more to it than this, but that's genuinely it. And then to run it, you either use OpenTelemetry instrument command to wrap your call, or it works great in a Docker file too. Modifying your entry point script is a great way to quickly roll this out if you're already rolling your own internal Docker-based images. I mean, okay, but it's very, very little more than this. So that was the zero code auto instrumentation. But you're right. Let's get all this out of the way now, then look at the data and identify the trigger point of our incident. Here's how you might add manual instrumentation to your app to enrich what was provided by the auto instrumentation packages. Up the top, we've got a couple of imports, and then we acquire a tracer. You can call that whatever you want. If you're putting it in an internal app or library, it's probably best to use the app or library's name. We'll get rid of that top bit so we can see the rest of the code a bit clearer. So we've already got a span that's created by the auto instrumentation, but we have to ask for that if we want to handle it ourselves. Alternatively, you could create a new span, but it's not necessary unless you specifically want to break out the execution from what the auto instrumentation was already giving you. We can then add some attributes to the span as we go. You don't need to worry about string building or anything like that, which might otherwise be needed to be solved if you're doing structured logging on your own. Just throw the values into a dictionary and pass it into the attributes that the span will do. I like to collect the attributes as the function progresses so that we can have the most complete picture if an exception was thrown at any point during execution. Speaking of exceptions, look, Ma, I wrote me some Pythonic code and sought forgiveness. It caught my exceptions. If something goes wrong, this will add that into the span and mark it as mark the span as having an error, and create a span event at the exact time the exception was handled by this code. That's everything. No more tricks up my sleeve. Sorry, one last trick. The Python decorator. Cute, huh? Whenever you call this function, a span will be created at its call and ended at its return. You can expand on this like with the previous auto-instrumented function, adding attributes or recording an exception. But it's great for wrapping loops. Your concern might be taking too long, or are interested in understanding, or particularly complex business logic functions you might want to get some transient attributes out of. I've kept you waiting as long as I can. So, what happened in prod? Let's take a look at the data in Honeycomb. So if we just do a basic count query for the last half hour, and we'll come and have a look at the data here. We can see here, if I expand one of these, this is the representation of a single span. We can see it has some attributes that we talked about, like the trace ID, the span ID, the trace parent, the time, some fields we might have expected, but in this case, these are the attributes that exist for that particular span. We can have a look at other ones and see other kinds of fields that they might have. If we click into one of these, we can see them put back together as the trace waterfall, which sort of clearly shows the parent-child relationship and the sort of times being taken. It's no surprise, for example, that the longest time out of this particular request spent was waiting on the database. That's just CRUD applications for you. It's also interesting to note that seemingly repeated set and select statements here, or spans. If we take a look at the library being used for each of those, we can see we get one from SQL Alchemy and one from MySQL Client. So we probably didn't need both auto instrumentations coming along. And if this were a real production system, you'd probably only use one of those, right? The one that best met your needs. If we come back to this query, we're interested in finding out what happened, right? So I like to look at a heat map of the duration milliseconds and a heat map of the log10, the duration milliseconds. We're also going to look at only the root spans, so that then we only get sort of that top level of each request shown in our results, and we'll group by HTTP status code, so that we'll get a split on which ones were successful and which ones were errors, as well as being able to see the sort of spread of the times taken. All right, so I think here's where we had our incident, just coming up on half an hour ago. This first graph here, like I said, is the count, and it's broken down by the status code. So we can see these ones were 500s, and these ones were HTTP 200 statuses. We've got a couple of 201s there as well, sort of scattered throughout. And then looking at the heat map graph, the shading here represents how many results at any particular value along the y-axis, and then the x-axis is the time that those events occurred at. So we can see that things were pretty fast, and then all of a sudden they were not so fast. If we zoom in on this sort of time range a bit, we'll be able to better sort of see what was happening there. So one of the things that we can do based on that grouping that we've done is we can ask Honeycomb to compare all of the 500s to everything else returned by the dataset using bubble up. So if we do that, and it will sort all of the attributes returned in that result set by those which are, I don't know the right term for this, most different first from the baseline. And so we can see all of the 500 error responses were an error. That's not a huge surprise. And everything else is sort of, probably a pretty even mix of things. If we come down and look at our manually instrumented fields, we can see that our customers were pretty evenly impacted by this across the board, right? Like there's no customers that stand out here. So what went wrong then? Well, we can see that there was a few requests that sort of hit first and seemed like they were slower So we can draw a box around these ones and say, just tell me about these ones, and see what was wrong or different about those. So again, we can see that all of those were errors versus just over half of the rest of them having an exception. If we come down again to look at our customer ID being recorded here, look, just the one customer being impacted right at the front there. So let's take a look at one of these traces. We can click on the heat map and jump into a trace that matches that point on the graph there. Yes, as we suspected, we waited for a minute on the database, and then the database gave up. And we can see that normalized query there, which looks the same as the query we expected to be running. Interesting. So there was something about customer ID number 60, and it also had such a low offset compared to the others. But wait, wasn't our new customer only number 59? Yeah, but we needed to have a fake customer for our synthetic monitoring, so we're really our own customer number 1. And it turns out they don't have much traffic. I bet that's a really quick query when there's only a single row. So let's look at our largest customer compared to our newest. Well, that's a bit of a disparity in volume of data, and probably where the data sits in the table. One's right at the start, one's right at the end. Well, there's your problem. I don't know much about databases, but I know you typically want to avoid a table scan. I bet these queries take forever to return, given the chance. So I've just pushed a new version of the app using what we've just learned about the query plan being less than performant for our newest customer. And how their new devices aren't even able to get up off the ground using our service. And we can see from the metrics, the system appears to be performing a little bit better now. We've had a bit of an increase in average response time, but almost no change in sort of the spread of statuses returned, right? Like that graph is nice and green. We like green graphs. That's good. Small aside possibly to make here is that this is a really contrived example where I had to cap the query timeout and the number of connections to the database to cause this to be a problem. But left uncapped, this is the sort of thing that has the potential to crash your database instance if your compute were left to scale up while this went on, and probably wouldn't fit within the confines reliably of a talk to give in this format. So I hope you've enjoyed this look into observability and OpenTelemetry, and that you'll be able to give it a go, give it a try in some of your trickier systems. Thank you.